Hello everyone, welcome to this session on synthesis and RTL coding. We were looking at combinational logic optimization and sequential logic optimization in the previous session. So there's one more interesting optimization that happens during the synthesis that's called as unused output optimization. Okay, it's called as unused output optimization. We will see what we mean by that. So let us look at this code. The code is present in your directory, the same directory only here. The code name is counter_opt. Let us look at this code. Basically, this module is accepting a clock, reset, and it's generating output called Q. There's a signal internal to it, which is a register, 3-bit signal called count. And we are writing always at passage clock, comma reset. If there's a reset, the counter is initialized to 0, else the count is incremented. So basically this code, if I look at just this portion of the code, it's a up counter. Whenever there's a reset, it resets to 0, otherwise it just counts up. 0, 1, 2, 3, 4, 5, 6, 7, again 0, 1, 2, 3, 4. Why it rolls back after 7? Because it's a 3-bit signal, correct? So it cannot go beyond 7. Again it rolls back to 0, 1, 2, 3, 4, 5, 6, 7, like that. Okay, so let's try to draw it. So I have a 3-bit up counter. I have a 3-bit up counter. So this is what I'm calling it as count of 2:0. I have a clock. I have a reset. Now, this count basically has 3 bits, correct? Bit 2, bit 1, and bit 0. Correct? Now let us see what happens to this. Now, this is the code of the counter, but the final output Q is sensing only the count 0. It is sensing only the count 0. That means this output is what is coming out as the output Q. These two outputs are unused. They are not having any use. They are unused. Correct? They are not used. Why they are unused? That's the functionality of the code. That means a logic which is unused need not be present in the design. Correct? See, think about this. If this logic, if this is going to have some dependency which is going to affect my output, then this is needed. But this is no way creating any dependency on my output. Say for example, let us take two cases, case 1, case 2. Okay, case 1 is what we have seen. So Q is equal to count of 0. Okay, in another case I am saying Q is equal to count of 2:0 equal to 3 tick B100, something like this I write, for example. What it means here I am least bothered about what is value 1 and what is the value 2 here. Correct? Count of the count bit index 2 and count bit index 1, I am least bothered. I am just looking for count of 0. That's all. Correct? Whereas if I look at this, I am interested in some value of count 0, count 2, count 1, count 0. Correct? All the 3 bits are interested. So I am looking for a value of count 2 such that all the 3 bits of counter are taking a particular value. Only then I am generating the value of Q here. So here all the 3 bits are getting used. So I need all the 3 bits here. Correct? Whereas in this case, I don't need bit 2 and bit 1. Q is count of 0, and count how the count of 0 is. If I look at this, if I look at the up counter, how the count pattern is going to be 0, 1, 2, 3, 4, 5, 6, 7. Again it goes back to 0, 1, and so on, correct? Now this is my Q count of 0, correct? This is my count of 0. Now every clock cycle the bit is toggling, correct? This bit is toggling on every clock cycle. Kindly note, we will come to this. This is toggling on every clock cycle. And these two outputs are unused. These two outputs of the counter are unused, and my Q is just tapping from the count of 0. This is what we are seeing in the RTL code. This is just a case 2 is just an example. Case 1 is what we are seeing in the code. Now let us see what this is what I'm seeing in the code. Let's see what happens if I synthesize this. So I'm going to launch the uses for synthesis first. The moment we launch the synthesis, we will read our liberty, mylib, lib, sky. We read the sky 130 libraries, then we read the verilog file, which is counter_op.v. Correct? We will set our top module synth-top counter_opt. Something interesting we are going to see here. See, it has inferred only one D flip-flop, correct? We expected 3-bit counter. That means it should have inferred 3 flops, right? It is inferring only 1 flop. Let's see why it's so. Let's see. Now, what I'm going to do, we are going to synthesis. So we will do the DFF libmap -liberty mylib lib. Yep. Correct. Now we will do our actual synthesis abc-liberty mylib lib sky 130, and I'm going to do show. Let us see what it's seeing. Oops, we are seeing only one flop, as this was seen the synthesis report also when we did synth-top. There's only one flop. A 3-bit counter should have 3 flop, correct? We are seeing only one flop. And see, let us draw what it has done. Let us try to draw it here, what it has done. Let me draw it in a different color. So I see a flop. There's an active low, the flop is having active low reset, but we are using active high reset. This we have seen earlier also. So there's an inverter here. So that's fine. There's a reset here. Let us not worry about that. There's a clock. The D pin is coming from some logic. Let us see what it is. The Q pin is connected to the bit 0, which is the count, and that is what is coming as Q, the final output Q, correct? So this is my count of 0, which is coming out as Q, and also it is going to a inverter here. See, it's an inverter. The inverter is coming back to D. So this is like a toggle, right? See, this is like a toggling, right? It's always going to toggle. If you look at this, what it is going to do, see, think about a circuit where Q is not of Q, correct? That's what is happening. Q is not of Q. 0 is becoming 1, 1 is becoming 0. 0 is becoming 1, 1 is becoming 0. And this is what we expected as output, and this is exactly what is happening. And these two bits which were unused are completely optimized off. These two unused bits, because they are not connected to any primary outputs. See, this is the primary output, correct? It is not having any connection to your primary output. So these two outputs, that means any logic which is not having direct connection, which is not resulting in any relationship with primary outputs, will be optimized. I may have for a given module, I may have one or more primary outputs. If I have some logic which are nowhere related to my primary outputs, all those logics will be optimized away, like what we saw here. These two bits are optimized away. Now just quickly for experiment sake, let us do some experiment here and see. So this is what we saw, right? Let us keep this in our mind.